Assalamu alaikum everyone. This is lecture 18 and this is the last lecture for this week. Before I start the lecture, again the acknowledgement for all the resources that I am using for all of my lectures. No new announcement, the same announcement as the deadline for the homework is extended. Just one addition that you need to take the pictures or a scan of your homework solution and email it to me by the deadline. Number of topics are included in today's lecture, which are finite impulse response or FIR systems, infinite impulse response or IIR systems, stability, causality, pole-zero cancellation, computing YN, Z transform and Fourier transform, and ROC properties. You have already done most of these things in previous classes and previous chapters. However, today we will discuss them with reference to Z transform. So let's start with the first topic of finite impulse response systems. Okay, so we already know that the system function h of z can be written as the ratio of yz and xz, and it is in the form of ratio of two polynomials, the numerator polynomial of degree m with coefficients bk's and denominator polynomial of degree n with coefficients ak. And we also know that the numerator polynomial provides us with the zeros of the system function, which we will get if we factorize this polynomial, and the denominator polynomial provides us with the poles. So root of the numerator are the zeros of the system and roots of the denominator are poles of the system. In this case, we are also taking a naught to be 1, so that's why this summation is going from 1 to n instead of from 0 to n. Now let's discuss a special case in which ak is equal to 0 for k from 1 to n, or in other words, this whole summation in the denominator would become 0. So what will be the consequence of this case? We will have h of z, which will have all non-trivial zeros and no non-trivial poles. We can further write this expression as this thing in which I am just taking multiplying and dividing by 0 to the power m. So this polynomial of degree m would give me m zeros, which will be non-trivial, and this 0 to the power m is telling me that I have mth order trivial pole at z equal to 0. So since in this case all the non-trivial zeros are present and there are no non-trivial poles, so this system is also called all zero system, and this system's impulse response will always be finite length, so this is also called finite impulse response system. If you remember, we did the same system in the last chapter also, but we came to the conclusion by computing the h of n or impulse response exclusively. Here we just know it by looking at this particular page, because we know that if this is all zeros, then it will be something which is finite. Next we will move to infinite impulse response system, and I guess you would understand that infinite impulse response system should have poles inside it. In this slide we are discussing infinite impulse response or IIR system. We start with the same expression of h of z. However, in this case we are making all the zeros to be non-trivial by taking bk equal to 0 for k from 1 to m in the numerator. So the end expression will be b naught over 1 plus summation k from 1 to n a k 0 to the power minus k. And we are just making this from z inverse term to z form. In this case you can see that we have all the zeros are non-trivial zeros which will be at z equal to 0. So at z equal to 0 we will have nth order 0, and the roots of the denominator will give us n poles which will be non-trivial. So any such system which has non-trivial poles, all the non-trivial poles and no non-trivial zero is called all pole system, and its impulse response will always be infinite impulse response. We actually have done some questions in which we went from a single pole or double pole system to h of n, and we saw that the response comes out to be infinite impulse response. In most of the cases, we have non-trivial poles and zeros both available in h of z, and all of those, so they are called pole zero systems. And one thing but you need to remember is that whenever there is a pole available which is non-trivial pole, then the system response would be infinite impulse response in that case. Okay, next we will move to causal systems. So we already know the definition of causality based upon the impulse response of the system. We know that if the impulse response of the system h of n is 0 for n less than 0, then in that case the system is causal. And by now, by doing so many examples, we'll also know that if ROC of the Z transform is outside a circle of radius r, then in that case the system is causal. This is something important. We will see later on that causality and stability of the systems are very important when we are designing different systems. So the next property that we will talk about is stable systems. Again, we know the definition of stability with reference to the impulse response. We know that if this summation is less than infinity, then the system is a stable system. Now we will find the condition for h of z and for which the system would become stable. We know that the definition of h of z is simply this summation is, so if we are taking the z transform of impulse response, then we will just have this equation, and we know that for ROC we compute the magnitude of h of z. So we would like to see what should be the ROC of the h of z in order for the system to be stable. So I am taking the magnitude on both the sides, and then I am taking the magnitudes of h of n and z raised to the power minus n separately. One thing, this is actually copied and pasted from your book, and I believe that this equal to sign should be here and then this less than or equal to sign should be here, but it doesn't matter. What we are saying is that h of z magnitude would be less than or equal to summation of n from minus infinity to infinity magnitude of h of n multiplied by magnitude of 0 to the power minus n. Now let's suppose that I take z magnitude to be 1. Then what would happen? This term would become 1, and I will be left with this summation which is n from minus infinity to infinity h of n magnitude. And I know that for stable systems this term is less than infinity. So what does it show me? That if I take the Z transform on the unit circle by taking Z equal to 1, then in that case my ROC would be such that the system would be stable, because because this term would be equal to this thing which is less than infinity for a stable system. So we conclude that the linear time invariant system is bounded input bounded output stable if and only if the ROC of the system function includes the unit circle. This is one of the most important definitions that you would learn with reference to the system functions and Z transform. as you will see later on. Now let's look at certain examples of what happens when the systems are causal and stable, or either causal or stable. So before we move to the examples, let's try to answer the question: what should be the ROC if the system is both causal and stable? Let's look at the individual definitions and try to combine them together. We know that for causality, ROC should be outside a circle of radius r, where r is the location of the pole. And we have seen in the examples that if there are more than one poles, then in that case, for causality, the ROC should be outside the outermost pole. So if I plot it, it would be something like this. R is the location of the pole, and it can be greater than or less than 1. I am not actually restricting it to any number, but what I know is that if R, I have just one pole at R equal to 0, R at Z equal to R, then in that case my system would be causal if this is the ROC. And in this case I am not plotting the 0, which would be trivial 0 at Z equal to 0. For stability, we just saw that ROC must contain the unit circle for the system to be stable. Now the question is, what would be the relationship between this circle with radius r and the unit circle for the system to be both stable and causal? Okay, I would suggest you just stop the video for a second and then try to think about it. Okay, so I have two possibilities for the two circles to be combined in a plot. Either r can be greater than 1, or r should be can be less than 1, or which means that either this pole, the circle which is plotted on the pole location is bigger than the unit circle, or it is smaller than the unit circle. Now, in order for the system to be both causal and stable, the ROC must have both the properties, that the ROC is outside the circle of this radius r, and it must contains unit circle. I know we can see from these figures that only the plot B can have both of these conditions fulfilled. So what we conclude from here is that if the system has to be causal and stable, then poles or pole need to be inside the unit circle. Why? Because for causality, the ROC has to be outside the circle of outermost circle. Okay, so let's suppose if it is not the case, the one of the circles containing pole is outside the unit circle, then ROC would be not including the unit circle itself. And if I say that, okay, why not take the ROC to be outside the inner pole circle, then in that case that won't be the causal system. And in any case this is not possible, because in that case my ROC will contain a pole, which is not possible. So this is again one of the most important conclusion that you need to remember, that for a system to be stable and causal both, ROC, the unit circle should contain, or all the poles should be inside the unit circle. Okay, let's move to the examples which will be based upon this concept. Okay, so this is the first example of a system in which we would like to see if the system is both causal and stable. First of all, we are given with h of n, which is half n u raised to the power n, and I have plotted the impulse response here. Just by looking at the impulse response, we see that this is a decaying function. So if I sum up all the values, it would be less than infinity, which means it is stable, and causality can be seen from u of n. Now let's go to z domain. compute the Z transform, plot the Z plane, and then see if from there we can conclude the same thing. So h of Z in this case would be equal to 1 over 1 minus half Z inverse. The pole is at Z equal to half, and because the U of n was there, so and we know that the ROC would be Z greater than half. So if I plot the pole 0 plot, I can see that the system is both stable and causal because the ROC is outward, outside the circle of radius half, and it contains the unit circle also. So causality is shown by outwardness, and the stability is shown by unit circle being the part of ROC. Next example, in this case we are given with a system which has an anti-causal system, which we can see from this u of minus and minus 1, and this is unstable also because we can see that the magnitude of h of n is increasing. So if we sum it up till infinity, it will be 0, or it will be infinity. So let's plot the z-plane plot, compute the z transform, and then see can we conclude the same things from there also. Okay, so in this case again h of z expression would be same. However, the ROC will be z less than half, and we can see that this is not outward, so this is not causal, and it does not contain unit circles, so this is not stable also. Next example, this is a system in which h of n is 2n un. Again, this is a causal system but not stable. Why? Because the magnitude is increasing, and if I sum it up, it will go to infinity. So it is by just looking by h of n, I know that it is called a causal and unstable system. And now let's move to Z transform and plot it, and then see what we conclude from there. So again, the expression for the Z transform is 1 over 1 minus 2Z inverse. The pole is at Z equal to 2, and ROC would be Z greater than 2. And in this case, again, the ROC would be outward, so causal, and ROC does not contain the unit circle, so it is not stable. And the last example is the example when you have anti-causal system because it is from minus infinity to 0, and we can see that the magnitude is decreasing, so it should be stable because the sum should be less than infinity. And if you plot the Z transform, again the expression is same as the previous one, but the ROC has changed to Z less than 2, and so ROC is inverse, which means that it is not causal. However, the ROC contains the unit circle, so this is stable. So now you should have a very clear idea of what causality needs in ROC, what stability needs in ROC, and another thing that you must remember is that these two conditions are not necessarily for a system. A system can be only causal, a system can be only stable, or a system can be causal and stable both. So it depends upon the design of the system and other characteristics, that would it be causal, stable, or both, or neither maybe. Okay, now we will move to next part of our lecture. Okay, so next we will discuss another example. And why I want to discuss this example, because this is an example in which we have two poles available. So, and I would like to discuss with you what happens, under what condition would the system be stable, causal, or anti-causal. You are given with the system function, and then from the system function, after the partial fraction and everything, you would get these two expressions. I would advise you to do the partial fraction of this h of z yourself. before moving forward, and you should come up with this solution. Okay, so once we have, so what we know from here is that in this system we have two poles. One is at z equal to half and the other one is at z equal to 3. The first thing that the first part of the question is telling us that the system is stable. That is some information that is given to us, and we want to find what would be the value of h of n in this case. I would like you to just pause for a moment and then think about this thing. What should be the h of n? In this case, if it is a stable system, that it means that it should contain unit circle. So let's see how it happens. So if it is a stable system, then it must contain the unit circle, and which means that it cannot be causal, because in this case the ROC would be in the form of a ring from the pole at z equal to half to the pole at z equal to 3, because this is the only way that it would contain the unit circle, and h of n would be combination of right-sided or causal and anti-causal sequence, or it would be the both-sided sequence. Next question was what would be h of n or impulse response if the system is causal. So let's see. So, but what you need to remember, for causal, the ROC needs to be outside the outermost circle. So think about it. What would it be stable or not? Okay, it is not stable, because if we have ROC which is outside the outermost circle of radius 3, then it would not contain the unit circle. So this system is stable. And the next part was what would happen if you are given that the system is actually anti-causal, which means it is right-sided sequence. So in this case, the ROC should be inside the innermost circle. And think about it, would it be stable or not? Okay, no. Why? Because in the innermost circle is at equal to 0.5. So if ROC is inside this circle, then in that case it would not contain the unit circle, and h of n would be something like this. Now I believe that you have thoroughly understood the concepts of stability, causality, what it means for them to be combined together, and how the condition of one being true affect the possibility of the other. Next, we will move to a topic which is important, and important mostly when we deal with the designing of the filter or the systems, which is actually to see what happens when the poles and zeros are cancelled. We will discuss that example with the help, or we will discuss the concept with the help of some examples. So now we will talk about pole zero cancellation. So what actually happens is that if you have a pole at certain location and you place a zero there, then the pole will be cancelled by the zero. And and if you take the inverse Z transform, then definitely that term which was containing that pole would vanish. Sometimes it's important to cancel the poles, because we whenever we are designing a system, we want it to be stable and mostly causal also, but let's just talk about stability. So if you want to the system to be stable and there is a pole that is in the system, and you don't want it to be there because it is not making it is not letting you make the system stable, then you may introduce a zero at that location, and in theory it works, but practically we don't do that because of the reason that placing a zero at the location of pole is not exactly cancelling them out in practical implementation, because we are implementing these things in our machines, in our computers and other processing machines, and due to the precision issue, pole at let's suppose pole at z equal to 1.5 would not be cancelled at exactly by 0 at z equal to 1.5, and it may complicate the system more than making it stable. So we don't do it practically, but in theory we can design system in such a way that we would cancel a pole by placing a 0 in that particular location if needed. Okay, so let's just look at the example here in which pole and zeros are cancelled. Sorry, poles are cancelled by the zeros. So in this example, you are given with a difference equation in which you have some previous values of y and current and previous values of x also. I am not going to do the computation for h of z. We have done it in detail before in number of examples, and it's easy, but I would advise you to compute this h of z yourself, and it should come out to be this thing, this expression, again the ratio of two polynomials in the numerator and denominator. And we want to do the partial fraction, so we are computing the roots of the polynomial in the denominator. And then after doing the partial fraction, again I'm not going to do the partial fraction here, but the partial fraction would be okay, before doing the partial fraction, again we are um, multiplying it by z, or taking it in the form of z instead of z inverse. And by computing by placing z equal to half and z equal to 2, which are the locations of the two poles, we would find the values of a and b. And again I would advise you to do it yourself. However, here I am giving you the values. A would come out to be 5 by 2 and b would be 0. So this b equal to 0 is actually indicating that the pole which was at the location z equal to 2 is cancelled by some 0 in the numerator. So consequently, at the end of the day, our h of z would come out to be 1 minus 3 z inverse. And actually here we have factorized the numerator also. So the poles and the zeros at z equal to 2 would be cancelled, and we have 1 minus 3 z inverse over 1 minus half z inverse, and h of n would come out to be delta n minus this expression, which is actually a causal system. And if I go back from here to y of n, which is actually just replacing h by y and delta by x, then we can see that the y of n would come out to be half of y n minus 1 plus x of n minus 3 of x n minus 1. So this is actually showing that the system equation has also changed. But and the original system was stable, so this is also stable because of this half of n minus 1. But the thing is that we, as I explained earlier, we won't want to cancel because it can become unstable because of practical implementation of the system. Okay, next we will do another example in which we will compute y of n after starting with the difference equation. So you are asked to compute the response of the system with the given difference equation, this given equation, to the input signal x of n equal to delta n minus half of delta n minus 1. So we know that y of z is actually x of z times h of z. I can compute h of z from this difference equation, which will come out to be something like this. And x of z I can compute directly from x of n, this is this, and then when I multiply both of them I would get y of z, which is 1 over 1 minus half z inverse. And it actually, again, as you saw in the last slide, there was a 0 at z equal to 1 by 3, and there were a pole in h of z at the same location, so they are cancelled. And in this case actually the 0 in the is cancelled by the system. In the previous example, we saw that in that case, the poles and zeros cancellation was in the system function itself. So what we conclude from here is that the pole that is cancelled may be in the system um, response h of z, or it can be in the input x of z, and both of those cancellations would affect your system output or in the system differently and not advisable in practical scenarios. And from here y of n would come out to be this thing, which is something that you already know. Okay, this takes us to the last part of our lecture, which is um, almost over the last part of the lecture, which is actually computing the relationship between Z transform and Fourier transform. So we know that if we have a signal x of n, then the Z transform of that signal is written as summation from n minus infinity to infinity x of n z to the power minus n, which is x of z, and we can write zz as r of eg omega, and then this expression will become this thing. And you would remember the expression for the Fourier transform from your signal and systems class, and it was actually equal to x of eg omega, which is n from minus infinity to infinity x of n e minus j omega n. So if we compare these two equations, we can see that Fourier transform is just a Z transform taken at r equal to 1. So it means that if we are computing Z at the unit circle, then whatever answer we are getting is the Fourier transform. Another thing that you would remember is that for the Fourier case, the frequency axis was linear and it was from minus infinity to infinity. However, when we are mapping it on this unit circle, it is from 0 to 2 pi only. But again, that should not be an issue because Fourier transform is periodic, which means everything repeats after 2 pi. So when we are wrapping that linear axis on this unit circle, it is actually saying that everything is going from 0 to 2 pi and then the repetition again and again. So we are taking the whole long axis and mapping it on this circle. In this lecture, we will just remember this thing that Fourier transform is Z transform evaluated on the unit circle, and then in the next classes you will study about Fourier transform in detail. So to wrap up this lecture, at the end I will just talk about the properties of region of convergences, because you would have concluded from here that region of convergence is one of the most important thing when we are discussing Z transform. And then at the end we will just summarize whatever we learned during the 3 lectures. These are actually the properties of ROC. The first property is that ROC is a ring or disk. Disk, we have been calling it a circle. And it will be ring or disk in the z-plane centered on the origin. Okay, and the second property is that the Fourier transform of x of n converges absolutely if and only if the ROC of the z transform of x of n include the unit circle. You will study it in detail again in the next lecture. Then a very important property, the ROC cannot contain any poles. Fourth property, if x of n is a finite duration sequence, that is a sequence that is 0 except in a finite interval from maybe from n1 to n2, then ROC is the entire z-plane except possibly z equal to 0 and z equal to infinity. Next property is if x of n is a right-sided sequence, a sequence that is 0 for some n. Okay, so right-sided sequence meant that it may be causal or it may not be. Right-sided here means that it may be starting from 0 or it can start from somewhere before 0, but it is going towards the right. Then in that case, we know that the ROC would be outside a circle, which would be the circle for the outermost pole. Okay, and if it is the left-sided sequence, then it would be inside the innermost pole. I would like you to just ponder about these two points, that it would be including z equal to infinity and z equal to 0. And if you don't understand, you can actually read the Oppenheim book. It has explained this thing into detail, or try to think about it. And so what I am just saying here is that left-sided is not anti-causal. Specifically, it is something that is going till minus infinity because it is infinite in length, but it may be starting from 0, or it may be starting from 1, 2, or 3, which means that it may be starting from n greater than 0 also. And similarly for right sided, it may be starting from n less than 0. So in that case, we know that ROC should be inside the inner circle or outside the inside the innermost circle or outside the outermost circle, but z equal to 0 and infinity may play a part in there also. Then the next property is that the two-sided sequence is, if the two-sided sequence is an infinite duration sequence, then that is, which means that it is neither right-sided or not left-sided, or it is going from minus infinity to infinity, then ROC will contain the ring in the z-plane, bounded on the interior and exterior by a pole, and consistent with property 3, which means that it won't have any pole inside it. And ROC has to be a connected region, which means that it is not possible that I say that ROC is one circle here or one square here and another circle or square somewhere else. Okay, this takes us to the last slide, which is kind of which is connecting different things. For example, we started with difference equation, and I have given here a very simple difference equation, which is y of n is equal to a y of n minus 1 plus x of n. From here we can go to y of z, which is a z inverse y of z plus x of z, and then from there we compute the system function. From the system function, we know that the system is causal if we have given the ROC, and then we compute the frequency response, which is actually the system function computed at r equal to 1, which is h of ej omega, and it will be equal to 1 over 1 minus a e minus j omega, and we know that it would converge if a is less than 1. And then from this frequency response or system function, we can compute the impulse response, which is equal to h of n equal to a n un. Okay, so this is end of the lecture for this week. I hope you understand all of these 3 lectures, and by Sunday this week the next 3 lectures would be uploaded. Okay, thank you.